Hello, chemistry students. Mr. Diego here with a quick video on empirical formulas and molecular formulas. For this video, you need a periodic table and you're going to need a calculator. So before we get into the calculation piece, let's just talk about definitions. So an empirical formula is the simplest, I'm going to underline the word simplest, whole number ratio of atoms present in the compound, and a molecular formula is the actual ratio of atoms present in the compound. So to help drive this point home, let's just look at some examples. So an example of an empirical formula would be CH2. I can't simplify this ratio anymore. So I have a 1:2 ratio between my carbons and my hydrogens. So this would be an example of an empirical formula. It is in simplest terms. Examples of molecular formulas would be things like C2H4, C3H6, and C4H8. Notice that in each of these examples, so in C2H2, so dicarbon tetrahydride, I would have a 2:4 ratio. And in tricarbon hexahydride, I have a 3:6 ratio. And in tetracarbon octahydride, I have a 4:8 ratio. And hopefully you can see that all of these end up simplifying into a 1:2 ratio. So all of these examples are derivatives or multiples of my empirical formula CH2, so carbon dihydride. So why is this important and why do we care? Well, when we're thinking about molecules and we're thinking about ratios, a 1:2 ratio of carbons to hydrogens is significant. It leads to different physical and chemical properties. Excuse me. So even though each of these examples of molecular compounds are slightly different and will have slightly different properties, they'll all kind of revert back to some of the similar properties found in carbon dihydride. Think of it like siblings. Like everybody's a little bit different, but you have the same genes and you have the same characteristics. All right, so when we talk about empirical formulas, there's 3 steps that you have to do. So in step number 1, very simply, we're going to convert to moles. So whatever information I'm given, I'm going to convert to moles. Step number 2, I'm going to divide by smallest number of moles. And in step number 3, I'm going to construct simplest whole number, and that's key right here, whole number ratio. So when we write our empirical formulas, we can't have any fractions and we can't have any decimal points. Okay, so what I'm going to do is I'm going to jump over to our practice worksheets. And hopefully you'll see this pop up here in a minute. There we go. Just a little bit of lagging. And we're going to go through doing the empirical formulas for problem number 1 and for problem number 2. So notice in problem number 1 and problem number 2, we have a little bit different variation when it comes to the data that's provided. So in question number 1, it gives us what's called percent compositions. So I'm told that some compound has a percent composition of 26.4% carbon, 3.3% hydrogen, 70.3% oxygen. We actually see this quite frequently in analytical chemistry, and you saw it in the analysis of the Martian atmosphere activity, because this type of data is produced from a machine called the mass spectrometer, which is a pretty common machine used by chemists to determine the composition of unknown substances. So don't get fooled or thrown off by the percentages. The second one is simple grams. So if I have a sample and I actually count out the grams. So these are the two ways that you're going to see data presented when we're talking about empirical formulas. So let's tackle question number one first. So in our steps, we have 3 steps. So number 1 is, just to review, convert to moles. Step number 2, divide by smallest number of moles. And step number 3 is to construct our simplest whole number ratios, or essentially create my empirical formula. So what we have to do is we have to, like, I can't convert a percent to moles. Like, there's no conversion that we talk about that goes from a percent to moles. But we do have a conversion that takes us from mass to moles. And by using the molar mass, we're able to convert from the mass of one substance to moles of that substance. So what I have to think about is, how do I get this percentage into mass? And if you really think about it, what percent composition is saying is that if I have a sample, if 26.4% of it is carbon, 3.3% is hydrogen, and 70.3% is oxygen. Since it doesn't tell me the size of that sample, I can make up any sample size that I want. And what would be the easiest sample size to think about? Well, if I think of my sample size as 100 grams, and if 26.4% of 100 grams is carbon, then that means that I have 26.4 grams of carbon. And if 3.3% of my 100 gram sample is hydrogen, then I have 3.3 grams of hydrogen. And I would have 70.3 grams of oxygen. We can do this because it doesn't specify in the problem what our sample size was. If it did tell us what the sample size was, like it said that the sample size was 30 grams, then I would have to take 26.4% of 30 to figure out the number of grams. But to do this calculation, do empirical formulas, I have to start with grams to be able to do my calculation. Okay, so for step number 1, I'm going to convert everything to moles. So let's just think about it real quick. My conversion factor, let's do the conversion factors for each. So my conversion factor for carbon would be 1 mole. Carbon is equal to 12.01 grams. Carbon, I can find that from the periodic table. My conversion factor for hydrogen, 1 mole hydrogen equals 1.01 grams hydrogen. And my conversion factor for oxygen is 1 mole of oxygen is equal to 16.00 grams of oxygen. Once again, these come directly from the periodic table. If you're not understanding how to do step number 1, then please go back and rewatch my video on mole conversions. Okay, so for carbon, I have 26.4 grams of carbon. I like to use the railroad track method, but you can use the fraction method if you want. I look at my conversion factor. I have grams of carbon above my cancellation line, so I want grams of carbon below. I have 1 mole on top. Okay. I have 3.3 grams of hydrogen. I'm going to set it up the same way. So I have 1 mole hydrogen over 1.01 grams of hydrogen. And then for oxygen, I have 70.3 grams oxygen. And I'm going to set it up the same way. So 1 mole of oxygen over 16.00 grams of oxygen. What this allows me to do is it allows me to cancel out the units that I don't want, in this case, grams, and then leaves me with moles. So I'm going to go ahead and do my calculations. So 26.4 divided by 12.01, and I get 2.198. So I'm going to round that to 2.20 moles of carbon. And 3.3 divided by 1.01 gives me 3.267. So we'll call that 27 moles of hydrogen. And 70.3 divided by 16 gives me 4.393. So we'll call that 4.39 moles of oxygen. Right, so that's step number one. So step number two, and I'm going to do a little dotted line here so we can keep everything separate. In step number two, I'm going to look at my values from step number one, and I'm going to divide all of my values by the smallest number of moles. In this case, the smallest number of moles would be my 2.20 moles of carbon. So I'm going to, essentially what I'm doing is I'm just creating ratios. So I'm going to take 2.20 moles of carbon, and I'm going to divide it by my lowest number, which is 2.20 moles of carbon. And 2.20 divided by 2.20 gives me 1, which makes sense. I should have a 1-to-1 ratio of carbon, since carbon is the lowest number. Some people will skip this step. I like to do it just to make sure that I'm good on everything. Okay, the next one is hydrogen, so 3.27 moles of hydrogen. And I'm going to divide that by 2.20 moles of carbon. And when I do that, I get 3.27 divided by 2.20, and I'm going to get 1.486. So we're going to round that to 1.49. So essentially, I have 1.49 hydrogens for every 1 carbon, and 1 carbon per 1 carbon. So just we're making some ratios, okay? And the last one, 4.39 moles of oxygen divided by 2.20 moles of carbon. And when I do that, 4.39 divided by 2.20, I get 1.995. So we're going to call that 2. So I'm going to have 2.00, and essentially that's oxygens per 1 carbon. Okay, so the last step is I'm going to create my ratios. So I have a 1. So essentially, I can go ahead. I'm actually going to delete this bottom part. I just had it there to show you that we're creating a ratio. So essentially what I'm going to do is I'm going to use these numbers, the number from step number 2, and that's going to give me the subscript for my ratio. So I have 1 carbon, I have 1.49 hydrogens, and I have 2 oxygens. Okay, so by definition, if I scroll up, we're going to construct the simplest whole number ratio. Well, right now, I don't have a whole number. I have 1.49. So what do I have to do? Well, here's some rules for you. So if my number is 0.85, so in step number 2, if my number is 0.85 or greater, then I'm going to round up. If my number is less than 0.15, I'm going to round down. So let's just say that when I did the moles of hydrogen divided by the moles of carbon, if I got a number like 1.15 or 1.14, I would just round down my ratio to 1. Okay. In the middle, if my value is close to 0.5, I'm going to multiply all of my subscripts by 2. Okay, if my value is close to 0.25, I'm going to multiply all of my ratios by 4. And if my value is close to 0.75, I'm going to do the same thing. I'm going to multiply by 4. And here's why. So 0.25 is the same thing as saying 1/4. How do I get rid of this fraction? Well, I multiply everything by 4. Okay. If I have something close to 0.33, you probably guessed it, we're going to multiply by 3. And if I have something that's close to 0.67, I'm going to multiply by 3. So what I like to do is I like to leave my empirical formula with my non-whole number in it so that I make sure that I don't mess up on this step. So I like to, when I go from step number 2, which is right here, to step number 3, what I like to do is I like to write it in properly so I can see that I have a non-whole number. Well, 1.49 is almost the same thing as 1.5. So what am I going to do? Well, I'm going to multiply this entire formula by 2. So what that gives me is now I have 2 carbons, so I have C2. And now I have 2 times 1.49 or 1.5. So 2 times 1.5 gives me 3. And now I have 2 times 2, which is going to give me 4. Notice, can I simplify this? Can I divide any of these subscripts by a single number other than 1? No. So this is my simplest formula. So this is my empirical formula. Right, so a lot of work, right? So let's look at question number 2. So question number 2 is a little bit easier. So question number 2, all of my information is already in grams. So my conversion factor, we've already used these. So 1 mole of carbon is equal to 12.01 grams of carbon. And 1 mole of hydrogen is equal to 1.01 grams of hydrogen. So step number 1, I'm going to convert to moles. So 81.8 grams of carbon divided by, or multiplied by my conversion factor. So I have 1 mole of carbon on the top. 12.01 grams of carbon on the bottom. Grams of carbon cancel out. 81.8 divided by 12.01 gives me 6.81 moles. Okay, so I have 18.2 grams of hydrogen. And I'm going to use my mole conversion. So 1 mole of hydrogen is equal to 0.1 grams of hydrogen. Grams of hydrogen cancel. 18.2 divided by 1.01. And I get 18 point, we'll call that 0.02 moles of hydrogen. Okay, so that's step number 1. Okay, in step number 2, I'm going to divide by the smallest number of moles. My smallest number of moles is 6.81, so 6.81 moles of hydrogen divided by 6.81 mole, sorry, not hydrogen, that's carbon. Carbon divided by 6.81 moles of carbon gives me a 1, and 18.02 moles of hydrogen divided by 6.81 moles of carbon, 18.02 divided by 6.81, and I get 2.65. All right, so in my next step, I'm going to make my whole number ratio. Well, let's look at this, okay? So is this number greater than 0.85? Sorry, you can't see it on the screen right now. The 0.65, is this number greater than 0.85? No, so I'm not gonna round it up. Is it less than 0.15? No, so I'm not gonna round it down. So it's gotta fit somewhere in between. So I'm just gonna write my formula. So I have C, and then I have H 2.65. Okay, well, if I look up, where is 0.65 closest to? Well, it's closest to this 0.67 value. So it's closest to this value right here. So what does that mean? Well, it means that I have to multiply my entire formula by 3. So when I do that, I get C3. And when I multiply 2.65 times 3, I get 7.95, or roughly 8. So my formula would be C3H8. And that is my empirical formula. So I'm going to stop the video here. So we've gone through the steps for figuring out empirical formula. So 3 steps: convert to moles. Once you convert to moles, divide by the smallest number of moles. And then once you've done that, you're going to construct your empirical formula. The biggest thing and the trickiest thing is if it doesn't work out to whole numbers, you have to use this information. So you need to, if it's above 0.85, you need to round up. If it's below 0.15, round down. And then think of it in terms of fractions. So 0.25 and 0.75 are factors of 4, so I'd multiply by 4. 0.33 and 0.67 are like factors of a third. So we're going to multiply by 3. And if I have 0.5 or something close to 0.5, then I'm going to multiply by 2. Right, I'm going to stop the video here. If you have any questions, please let me know.